Welcome to Learning Outcome 4, where we explore the properties of engineering materials and how they decide what each material is good for. We'll look at how materials behave mechanically, thermally, electrically, and magnetically, and see why the right property gets matched to the right job. Let me outline where we're going. The central idea is that engineers pick materials by matching properties to the demands of the job. We'll study how solids behave under load, stress, strain, and stiffness, and the key laws behind them, Hooke's law, and the modulus of elasticity. We'll compare metals, polymers, and ceramics across 5 families of properties, and you'll solve numerical problems, stating the principle each time. And every idea ties back to a real product, from bridges right down to bottle tops. Let's define our starting terms. Force is a push or pull on a body measured in newtons. Stress is the force carried per unit area of cross-section measured in pascals. Strain is the change in length divided by the original length, so it's just a ratio with no units. Elasticity is a material's ability to spring back to its original shape once the load comes off, and stiffness is its resistance to deforming in the first place, measured by the modulus of elasticity, E. Let's survey the main mechanical properties. Strength is the stress a material can carry before it fails. Stiffness is how little it deflects under a given load. Ductility is how much it can stretch before it breaks. Hardness is its resistance to scratching, denting, and wear. And toughness is the energy it can soak up before it fractures. Between them, these properties decide whether a material belongs in a beam, a spring, or the cutting edge of a tool. Let's start with Hooke's law. For an elastic material, the extension is proportional to the force applied. Pull twice as hard, and it stretches twice as far. We write it as force equals K times X, where K is the stiffness constant in newtons per meter. But there's a catch. This only holds up to the limit of proportionality. Push beyond that, and the force against extension graph starts to curve. Springs, wires, and structural members all obey Hooke's law under light loads. And it's the foundation on which stress, strain, and the modulus of elasticity are built. Let's work an example. A spring stretches by 15 millimeters when a 16 Newton force is applied, and we want its stiffness, and then the extension under 90 newtons. First, convert the extension to meters. 15 millimeters is 0.15 meters. By Hooke's law, the stiffness K is force over extension, 60 divided by 0.05, which is 4,000 newtons per meter. Then for a 90 Newton force, the extension is force over K, 90 divided by 4,000, which is 0.025 meters, or 22.5 millimeters. Let's look at direct stress. Stress measures how concentrated a force is over the area carrying it, and it's simply force divided by area, with force in newtons and area in square meters. The unit is the pascal, where 1 pascal is 1 newton per square meter, though in practice engineers often work in megapascals. A handy fact is that 1 megapascal equals 1 newton per square millimeter. The lesson is intuitive. A thin rod carries a higher stress than a thick one under the same force, and the principle is always to keep the working stress safely below the material's strength. Let's calculate a stress. A steel tie bar has a cross-sectional area of 200 square millimeters and carries a tensile force of 20 kilonewtons. First convert. 200 square millimeters is 2 times 10 to the minus 4 square meters, and 20 kilonewtons is 2,000 newtons. Direct stress is force over area, so 2,000 divided by 2 times 10 to the minus 4, which works out at 100 times 10 to the 6 pascals, that is 100 megapascals, or equivalently 100 newtons per square millimeter. Now for strain, the partner to stress. Strain measures how much a material stretches relative to its own length. The change in length divided by the original length. Because both lengths are in the same units, strain has no units of its own. It's often a very small number, something like 0.005, which you might also hear called 500 microstrain. Tensile strain lengthens a member, while compressive strain shortens it. The neat way to hold the pair in mind is this. Strain tells you about the deformation, while stress tells you about the internal loading. Let's find a strain. A tie bar 2.5 meters long stretches by 1.25 millimeters under load. First, convert the extension to meters. 1.25 millimeters is 0.25 meters. Strain is the change in length over the original length, so 0.95 divided by 2.5, which comes to 0.5. That's dimensionless, and you could equally call it 500 microstrain. Let's bring stress and strain together in the modulus of elasticity, E, which measures a material's stiffness. It's defined as stress divided by strain, the gradient of the straight, elastic part of the stress-strain line. Its units are pascals, and for metals the values are large, typically hundreds of gigapascals. Steel comes in around 200 gigapascals and aluminium about 70, so steel is roughly 3 times stiffer. A high E means very little deflection under load, which is just what you want in a structure. And crucially, E is a property of the material itself. It doesn't depend on the size of the part. Let's tackle a fuller example. A steel rod 3 meters long and 20 millimeters in diameter carries a tensile force of 50 kilonewtons. And with E of 200 gigapascals, we want the stress and the extension. First, the area, PID squared over 4, with D of 0.020 meters, gives about 3.142 times 10 to the minus 4 square meters. The stress is force over area, 5,000 over that, which is about 159.2 megapascals. The strain is stress over E, 159.2 times 10 to the 6 over 200 times 10 to the 9, roughly 7.96 times 10 to the minus 4. And the extension is strain times length, 7.96 times 10 to the minus 4 times 3, about 2.39 millimeters. Let's distinguish tension from compression. Tension pulls a member apart, so it stretches and gets longer. Compression squeezes it, so it shortens under the load. A tie is a member in tension, while a strut or a column is in compression. The very same formula, stress equals force over area, applies to both. There's one extra thing to watch though. A long, slender member in compression can also buckle sideways. As a picture, think of a crane cable, which is a tie, versus the ram of a jack, which is a strut. Let's turn to shear. Unlike direct stress, shear acts along a surface rather than at right angles to it. Shear stress is force over area, but here the area is the one resisting the sliding, and the shear strain is the angular distortion of the material, written gamma. This is exactly how bolts, rivets, and pins tend to fail. They get sheared across. The key principle is that the sheared area is the cross-section straight across the fastener. And it's not always failure we're avoiding. Cutting, punching, and stamping all rely on making shear happen deliberately. Let's calculate a shear stress. A single bolt of diameter 10 millimeters carries a shear force of 8 kilonewtons across its cross-section. First, the area, pi d squared over 4, with d of 0.010 meters, gives about 7.854 times 10 to the minus 5 square meters. Shear stress is force over area, so 8,000 divided by that, which comes to about 101.9 times 10 to the 6 pascals, roughly 102 megapascals in the bolt. Let's read a stress-strain graph because it tells the whole story of a material. The first part is a straight, elastic region that obeys Hooke's law, and its slope is the modulus E. The elastic limit is the point where permanent deformation sets in. Keep loading and you reach the ultimate tensile strength, the highest stress the material sustains. Past that peak, the specimen necks, thins locally, and then fractures. A ductile metal shows a long, drawn-out curve, whereas a ceramic snaps with almost no warning at all. Let's fix the terms from that graph. The limit of proportionality is the stress up to which stress and strain stay in proportion. The elastic limit is the largest stress before permanent plastic deformation begins. The yield point is where the material suddenly stretches noticeably for very little extra load. The ultimate tensile strength is the highest stress it can withstand before failing, and ductility is its ability to be drawn out or stretched before it breaks. Let's move beyond mechanics to thermal properties. Thermal conductivity is how readily a material carries heat. Metals conduct well, which makes them ideal for heat sinks and cookware, while ceramics and polymers insulate, which is why they suit handles and linings. Then there's thermal expansion. Materials grow when heated and shrink when cooled, and that's why bridges and railway lines are built with expansion gaps to absorb the movement. Finally, the melting point sets the maximum safe operating temperature for a material. Now, to electrical properties. Electrical conductivity measures how easily current flows through a material. Copper and aluminium conduct well, so they're the natural choice for wiring, and for a conductor, the current and voltage are linked by V equals IR. Polymers and ceramics, by contrast, are insulators used for sheathing and casings, and some ceramics do sterling work as insulators on high-voltage power lines. Whether you want a conductor or an insulator comes down entirely to the job the product has to do. Let's cover magnetic properties. Ferromagnetic materials, such as iron and steel, are strongly magnetic, and that's what makes them right for motor cores, transformers, and relays. Most polymers and ceramics, on the other hand, are non-magnetic, and so effectively are aluminium and copper. There's a further distinction worth knowing. Soft magnetic materials magnetize and demagnetize easily, which suits changing fields, while hard magnetic materials hold on to their magnetism and become permanent magnets. Let's compare metals and polymers directly. Metals are dense, typically between 2,700 and 8,000 kilograms per cubic meter, with high strength and high stiffness, so a large E. They conduct heat and electricity well. Many are ferromagnetic like iron and steel, and they're ductile and tough, taking well to machining and welding. Polymers are the near opposite, low density, around 900 to 1,400 kilograms per cubic meter, lower strength and low stiffness. They insulate against heat and electricity, they're non-magnetic, and they're light, corrosion-resistant, and easily molded into shape. Now, let's set ceramics against metals. Ceramics have a moderate density but are extremely hard and stiff, with high compressive strength, though they're brittle in tension. They're excellent thermal and electrical insulators, and they withstand very high temperatures, which is why we use them for tiles, insulators, and cutting tips. Metals are generally denser than most ceramics, but they're strong in both tension and compression. They conduct heat and electricity well, and they soften and melt at lower temperatures. That's what makes them right for structures, shafts, and fasteners. Let's see selection in action. You always begin by stating the requirement: strength, stiffness, weight, cost, the operating environment. For an aircraft skin, aluminium gives good strength at low density. For a cutting tool tip, a ceramic gives hardness and heat resistance. For an electrical cable, copper offers high conductivity together with the ductility to be drawn into wire. And for a drinks bottle, a polymer is light and easily molded. The single guiding principle is to match the dominant property to the product's job. Let's finish the calculations with a density problem. An aluminium block has a mass of 0.500 kilograms and a volume of 1.85 times 10 to the minus 4 cubic meters, and we want its density to confirm it really is aluminium. Density is mass over volume, so 0.500 divided by 1.85 times 10 to the minus 4, which comes to about 2,703 kilograms per cubic meter. That matches the standard figure for aluminium, around 2,700, so the material checks out as aluminium. Let's test yourself. First, can you state Hooke's law and write down its equation? Second, A rod of area 400 square millimeters carries 40 kilonewtons. What's the direct stress in megapascals? Third, why is the modulus of elasticity a measure of stiffness rather than strength? And fourth, can you explain the difference between the elastic limit and the ultimate tensile strength? A few more to try. First, which group of materials would you pick for an electrical insulator, and why? Second, can you name a product that relies on a material being ferromagnetic? Third, a bolt of area 5 times 10 to the minus 5 square meters carries 6 kilonewtons in shear. Find the shear stress. And fourth, why are expansion gaps built into railway lines?